So in the last video, we did a bit of derivation relating to Ponchon-Savarit and the Ponchon-Savarit diagram for distillation column design. We went through the similar triangle proofs to prove how the Ponchon-Savarit diagram actually calculates the vapor compositions of each stage through that methodology. And today what we're going to be doing is we're going to be using Python to generate a Ponchon-Savarit diagram given a few base parameters. So what I have here is a bunch of imports. I have laid out our problem here with some parameters, a reflux ratio, recovery. We also have our distillate composition. We have our system as isopropanol water, a feed rate of 1 mole per second. We also have our feed composition. We have our quality, our feed quality, as well as atmospheric pressure. We also have a bunch of functions that I have actually coded out in a previous video. These are all just the NRTL model, so non-random to liquid model for our bubble pressure and bubble temperatures, as well as our dew properties, as well as an interpolating section over here for us to be able to pull some values to be used in enthalpy calculations, so on and so forth. So I think a good place to start would be starting to calculate some more information given what we have already, right? For one, I can say something about the feed. So the feed is going to have to be our bottoms plus our distillate. And since we don't know either of those items yet, we can go ahead and calculate it. So we could go ahead and we could probably say something like, well, maybe let's calculate our distillate flow rate, right? So this is going to be our feed times our feed composition times our recovery. So this is whatever is going to be showing up in our distillate. So far we have this in terms of just our so this would be our moles per second. This is a ratio. This is also a ratio. So all of this will go over our distillate. So I think maybe I'll put this all under here. So now we should have a definition for our distillate feed rate. And our bottoms rate should probably look something very similar. Something like this. And instead of having this recovery in the distillate, it would be 1 minus that, as we are not as whatever is not being recovered in the distillate needs to be recovered in the bottoms. And then this would be over our XB. And now our XB, this would need to be calculated by, so let's change up our strategy a little bit here. What we know from this is, since we have this relationship and we know our feed and we also know our distillate's flow rate, what we can do is we can say something like our bottoms is equal to our would be equal to our feed minus our distillate. So something like this would give us the definition for B. And instead of having that to calculate our B, we can calculate the composition of our bottoms, and then we would divide that over like that. So this should give us our distillate flow rate, our bottoms flow rate, as well as our bottoms composition. So we already know 3 more parameters that we previously did not know about. So with this reflux ratio, actually, now what we can calculate is the vapor leaving our first stage, which is useful because we're going to be needing that to calculate the heat values. So that would look something like, so we have our distillate flow rate, and then remember from our mass balance that we had done a while back, I'm talking about distillation column design, it is going to be our reflux ratio plus 1. So it would have looked something like the vapor flow rate is equal to RD plus R, and then you just pull, or sorry, RD plus D, and then you pull out the D to get this final form. Now, the reason that I pulled these Akima values here is so that we can, instead of using polyfits, this Akima gives us a more accurate interpolation function for us to be able to use these temperatures, these compositions, to calculate our enthalpies. And that's exactly what I'm going to do here. So first things first, let's start with the feed. So this is enthalpies of the feed. And we have a library that we can pull from. This is going to be our, so we're going to have to pull an array. And that's going to be our isopropanol and our water. And then we also need to give it a temperature. And now you'll notice that we have this, we do have this TX Akima over here. And we're able to use that to pull our, to pull that temperature that we need to calculate this enthalpy. So let's go ahead and use that. So TX Akima for this one will be 4Z. So that's our feed enthalpy. And if we do pull this, we get this value in joules. So now we can do something very similar for our, we can start with our distillate if we want. So this is going to be, instead of Z, XD. And then one more time for the bottoms. So here, HB, XB. There we go. So this is everything that we should need in order to calculate the enthalpies for our feed, our distillate, and our bottoms. So now I want to pull my cooling power and my boiling power. So this QC and QB that we used earlier. What that's going to look like is I'm going to use that V1 that we calculated earlier, and I'm going to get the vapor enthalpy from that. And that's going to be for our distillate. And then the temperature at which I will be calculating that at will be that TY Akima next day, and then minus my distillate enthalpy. So that should do it for that cooling power, and that's all part of mass balances that we derived, part of what's going on up here. And so is this boiling that we are going to be using as well. So for one, we are going to have our feed times our feed enthalpy plus our we're going to have our, thinking about what's going in first. Well, why don't we just pull that up? So of course we're going to have a feed entering, and then we're also going to have this liquid also is going to be entering. So we're going to have a liquid. How do I want to do this? I think I'll just go overall. So we're going to have a distillate, so times our HD, minus our bottoms, which is linked to B times HB, and then plus QC, I think should do it, right? So these should be all the parameters that we can use. We're going to set up a couple equations for energy and mass balances for the rectifying section and the stripping section, and that's how we can calculate the tie-in lines as well as the Ponchon-Savarit lines. So I think I bunged this up a little bit, but it should be correct now. You see that we actually have to subtract that feed and add that boiler. And I think now we're in good shape. So the first thing I'm going to do here is I'm going to do this energy and mass balance for the rectifying section. And we're going to give it inputs of our yn plus 1. We're going to give it our hln and our xn. Right? Now, I think probably just xn over there. The thing that we want to calculate here is our enthalpy of our stage below. So we're going to go p.hv. I think Python is already trying to predict what we're going to do here. So I'm just going to let it autocomplete for me and see what happens. So we see that we're giving it input of our vapor mole fraction, and then also doing the interpolation sequence, the Akima interpolation sequence, given that vapor composition too. So that actually doesn't look too bad. Now in the return, we see that we have an energy balance on this side and a mass balance on this side. And what kind of ends up happening is we kind of have this cross multiplication idea going on here. So what do I mean by that? Well, we're going to multiply this side of our energy balance to this side of our mass balance. So if we go ahead and do that, so we have a QC over D. I'll pop this up on this other display here so I can see it. You will not be able to, but it is just me copying it down. So we have a QC over D plus HD minus HVN1. So here is one part times, and then our yn1 minus our xn. And then from this, we are going to subtract the other side. The other side looks like HVN1 minus HLN times, so this is our distillate composition minus yn1. And now, since we have this here, the stripping is going to look very similar. We're going to have the same inputs. We're going to have the same calculation for our enthalpy of the vapor from the stage below. All that's going to change is this return function that we have going on here. So now what we have is we have our HVN1 minus our HLN times our xn minus our xb minus our yn, or I'll do the enthalpy bit first. So let's do HLN minus yeah, I'll do this. We'll go minus HB plus QB over B times yn1 minus xn. So these should be the functions that we will use, and we will go ahead and perform this for as many times as necessary for the rectifying and the stripping. We're going to set up a conditional for that. So yeah, that is the direction we are headed in next. So now the next thing to do is we're going to have to start creating our loop to start storing values. So I'm going to initiate two arrays. We're going to have a y and 1s array. We're going to have an x and 1s array as well. And let's say for our first y and 1, it's just going to be equal to our distillate composition. Now, we start a loop, so we're going to say for I in range, let's say like 100 for right now. We want to calculate that akima, so we're going to go and say that our xn1 is going to equal our tx akima of our yn1. I believe that is correct. Where is it? Where did I put that? Here. Given an x, it'll give you a t. No, I want this x1 akima, actually, sorry. x1. And then I'm just going to pull the item from this. And what that'll do is it'll just pull the, it is not going to pull the second thing. Because when usually you pull something for an akima, so let's say, I'll just open up. So let's say x1 akima. Let's say I want to pull from xd. It's going to say the whole array is going to be input in. If you just pulled the item, what it does is just gives you the value inside. So it's a pretty useful little thing to know. And then what'll end up happening is that we are going to go ahead and we're going to append this to our xn1s. So xn1s dot append xn1. So now I'm going to throw in a conditional. And I'm going to say now if our xn1 that we calculated is somehow less than our bottom's composition, then we're just going to break out of this loop entirely and we're going to stop recursing. Also, I should be giving this first value over here to the y1s. Also, on the side, what I did is I flipped around the order of this return function here just to match up with the return sequence that we have here. Make sure we have continuity between the two, just so we're all on the same page. Then what we want to do is we want to calculate a liquid enthalpy, and that's easy enough. So we're just going to go ahead and we're going to give it the array of our composition. And that's going to be our xn1, 1 minus xn1, and then our akima, so tx akima, and that's going to be for xn1. Now, you can already start to see Python, it already started kind of guessing what we want to do next, and it is exactly correct. We want to start calculating the yn1 as well with this, now that we have calculated this enthalpy to be used with our functions that we described earlier. So I'm gonna go ahead and I'm gonna let, oh, where'd it go? I'm gonna let Python do its initial little guess here, and I'm gonna fix it up a little bit. So yes, we're going to have to do another conditional here. So now we're gonna say if our we're going to say if our xn1 is less than our feed, because that is the point to where we are going to cross over into our stripping section. So if it is less than that, what we'll do is we'll say our yn1 is going to be calculated using the stripping section of our function. And so we're going to have a lambda. It's going to give us, or it's going to say that we're going to give it an input of our yn1, or rather that's what we want to calculate. And we will go ahead and we will give it a bracket for which it can pull values from. And that is going to be from xn1 to yn1. And if not, so else, it will go ahead and it will use the rectifying section. But everything else should stay exactly the same. God, where? I'll figure all that out. And then what we'll do is we want to get the roots of these and go ahead and append. And then it should continue to recurse until we have all our values. Okay, I think the issue is that I just didn't have brackets around the array that I initiated. So now if I do that, it is happy. Now before we go off and start plotting and whatnot, I kind of want to take a look and see what my yn1s are. So as you can see, that those look like pretty reasonable values. And then we'll also look at our xn1s. Yeah, so those look pretty good. So one more thing that we need is we need the enthalpy of our vapor and the enthalpy of our liquid. So we need those lines that define the Ponchon-Savarit, and we use those triangles to calculate our vapor compositions, right? So I'm going to start two new arrays, exactly like that. And then I'm going to also say I want, let's say, I'm going to go my x's equals np.linspace. And I'm going to go from 0 to 0.999. And the reason I'm doing that is because I don't want to be exactly at 1. Otherwise, you might run into some issues. And I'll say I want like 50 points in between them. Right? So now I could say for x in x's, we want to append the akima. So maybe we could say so hv equals p dot hv, and then np dot array. Do I like that? Yeah, that looks alright to me, I think. So let's see y akima, and I will give it this x. And then same thing for my HL. I think that should be alright. And then, yeah. So now we can start plotting. So I'm going to go ahead and initiate a subplot. We'll add a scatter. And I'll go ahead and plot our out our HV and our HLs. So our X is going to be our X's that we set, and then our Y, I'll go ahead and make this my HVs. Mode equals lines. Go ahead and see if that works. Yeah, it seems to be working okay. I'm also going to name it, so name equals HVAP. And then this is going to be the exact same thing for the liquid, except we're going to be changing this to HLs, and we'll be changing this to H liquid. And boom, there we go. We have our line for our vapor and our line for our liquid. Then we'll go ahead and add another scatter, and this one's going to be pretty easy to do. So remember that first vertical line in the rectifying section that we gave it, we said that we defined the x as being as xd. So right now it's just giving us that 1 point there, but once we give it our y's that it corresponds with, so we could say that we want it to be at the distillation enthalpy and the distillation enthalpy plus QC over D, because that is where our point is. And there we go. We have our vertical line, and just change the mode. So here is where we can start to develop our Ponchon-Savarit diagram. So now let's go ahead, let's start our loop. So now what I want to do is a little bit something different. And what I'm going to say is that for each tuple xy in my zip of xn1s and yn1s, I want to add a scatter. So my x is going to be equal to my xy. And then my y is going to be equal to the respective enthalpies. So p dot hv, I'm going to go to p dot array. Well, I think this needs to be hl, and then, yeah, mp dot array. And then I'm going to give it my x and my 1 minus x. And then my tx akima. Right here. And then my p.hv. Basically this, but we're going to make it a y's instead. I'm just going to go ahead and see what this gives me. So there you go. These are our tie-in lines for our Ponchon-Savarit. I'm going to go ahead and I'm going to standardize this a little bit. So I'm going to say my mode is equal to dots. Dotted. That's going to be errors. I'll figure that one out. But definitely gonna have to make that gray. I guess I gotta set this mode equal to lines. Okay. So there you have it. These are our tie-in lines for the diagram. So now let's start creating the lines for our that show our equilibrium relationship. So, gonna go ahead and let's do the rectifying section first. So this one, instead of x and y, it's gonna be x and xd. Our y is going to follow this first part here. So I'm just gonna copy and paste this down. Then after that, it's going to be our HD plus our QC over D. Mode equals lines. And I'm going to make the line color, let's say green. I do like green. So this looks good so far, but there is an issue. And the issue is that it's, well, for one, I think we kind of screwed up these tie-in lines. They should be going the other way around. But the other thing is that it doesn't detect the crossover from the rectifying section into the stripping section, and therefore it treats everything as the rectifying section. So we need to set up a conditional in here that allows us to detect that there is a crossover into now our stripping section and start calculating it using our delta B correlation instead of our delta D correlation that is up here. So the first thing I'm going to do is I realize that my order is kind of messed up here. So I think if I swap these two, then yeah, this is more of what I expected. There's a little bit of weirdness going around here, but that'll change once we figure out what we're doing with the crossover region. I'm also going to change this line color to green to make sure that there's not a really off-putting color in the middle of all of it. Much better. So now what I'll do is I'm going to first set something called first line. And this is going to be a variable that we'll use later, and I'll show you why. And I'm going to set it equal to this false conditional. Now, what I'll say is if my x is greater than my z, if it's greater than my feed composition, then we will be in our rectifying section and we can plot it as if it were in the rectifying section. Else, what we're going to do, if our first line is equal false, so this will run a check on it, then we're going to make it true for the first time. First line equals true. So what has this done so far? Well, this has stopped our graph from going into our stripping section. But now, what about the line that'll connect our delta D point to this delta B point from our distillate to our bottoms? And the answer to that is simple, and it follows closely to well, I guess I did need that here. And then do that. Instead of now going from x to xd, this is going to go from x to xb. And this will work for the vapor side of things. Ty Akima. And this is going to be our bottoms enthalpy minus our QB over B. So making sure that we are going from Y to XB, and we are calculating the vapor enthalpies using our vapor mole fraction, using our Ty Akima, making sure that we're using the correct correlation. And now that we have changed all that, we have developed our Ponchon-Savarit diagram. This gray line down here although it looks like it's trying to pull another line from here. This is actually what we saw in the McCabe-Thiele diagram, where it was creating an extra staircase over, but it didn't necessarily go down to create another stage. This is for that reboiler down here. So if we wanted to get extra fancy, we could update our axes. And we can say we want our range go from 0 to our distillate composition plus, say, like 0.5. Maybe that's not exactly the right thing, but you know what? I guess that doesn't really matter. What matters is that we now have a nice Ponchon-Savarit diagram that kind of tells us the number of stages that we could produce in our distillation column as a function of our enthalpies and equilibrium compositions.